Last one, last Wednesday. This is the last Wednesday class lecture, Zoom style. Hopefully we'll be back in person. We'll see next semester. All right. So last class we particularly were interested in this topic. We also discussed a bit more on finding expected value using joint distributions and marginal distributions. And now we're heading into the world of joint probability distributions of functions of random variables. So this time you're given the joint distribution, joint density function between two random variables. And then you have this new set of random variables in terms of the other original random variables that you started with. So the question is, how do we find the joint density function? And so we utilize what's called the Jacobian. Now, without getting too crazy with this, the Jacobian is simply the determinant of a 2 by 2 matrix. And this matrix has two rows and two columns, and each entry is a partial derivative of the given functions of x and y. So we have partial derivatives, and we just take the partial derivative, just taking the derivative with respect to a particular variable. And we do so, and then we do the determinant, which is, in a way, you can think of it as a cross multiplication of the entries, and you subtract those products as such, as so. And then what we do is we use a formula, right, for this new density function, utilizing these new random variables. It equals the old density function divided by the absolute value of the Jacobian. And then once we have it in this expression, we have to solve for x and y in terms of u and v, and we just plug in. And after we plug in, we're done. Okay. I want to continue though with this particular example. So I'm going to take these pages here. So we found all of this, right? And now what I want to do is I want to find, so part B to this is find the domain for FUV. Now let's kind of let's remember what our original function was. F of x comma y is equal to 1 over x squared y squared. That's if x is greater than 1 and y is greater than 1, and it's 0 otherwise. Now we have this new, and of course we can do this xy thing. This is uv. Now we have this new joint distribution, which is 5 over 2u squared v. And now the question is, what do I put here for the domain? What values of u and v work? And then here it would be 0 otherwise. Now, how do we determine that? Well, didn't we find what x was in terms of u and v? It says x is what? The square root of u times v over 5. And so the square y is the square root of u over v. And so we know x is what? Greater than or equal to 1 from here. And we know that y is greater than or equal to 1. So we had these inequalities. If we study them a bit more, what information can we get from it? Well, we can get that the square root of uv is greater than or equal to 5, right? Let me just see, it's right, 5. Square root of uv is, let me see, hold on. Yeah, square root of uv is 5. I think I may have, let's see, this is 5, right? I'm just going back with solving for x and y. Just want to make sure that this is okay. Y is u over v, so we plugged in, yeah, this should be correct. And so what is uv then? uv is greater than or equal to 25. And then if you solve for this here, we get u over v is greater than or equal to 1 if we square both sides, right? And we can say that 5 u is, we can say that v or u is greater than or equal to v. Or we can write it this way, v is less than or equal to u. And at the same time, v here is greater than or equal to 25 over u. So v is greater than this, but then smaller than u. So v is in between u and 25 over u. So that would be our interval here. So v is between u and 25 over u. And then the question is, what is u? So when do they intersect would be the question. So if you look at v less than or equal to u and v greater than or equal to 25 over u, when do these inequalities have a when are they equal? They're equal when u is equal to 5, if you notice. If this is 5 and this is 5, then v is the same. So that means that u has to equal 5 at least. It can't be less than 5. So we say that u has to be greater than or equal to 5. So this is my domain for my joint distribution. So you have to play around a bit with the original variables, the x and y, and how x and y are defined in terms of the new variables, u and v. And there might be some inequalities here and there, but eventually you have to find what the new variables are in terms of the one of the new variables in terms of the other new variable. And here we found that v is between these two variables here, 25 over u and u. It's going to look a little strange. And that u has to be bigger than or equal to 5. Okay? Okay, so then the next thing is what would be the marginal density of u? Let's say I want to find the marginal density and I'm given this joint distribution. How would I find the marginal density? Integrate over v. That's right. That's right. So this is f of little u. This is the integral from negative infinity to infinity of what? Of f of uv over dv. Now, what's v in between? Do you see that? V is between 25 over u and u. And this is 5 over 2u squared v dv. But of course, we're integrating with respect to u. I mean to v. So our u in our integrand can be taken out. So this is 5 over 2u squared. The integral from 25 over u of 1 over v dv. Now, what's the antiderivative of 1 over v? ln, right? It's ln of v. And I'm evaluating that from u and 25 over u. So this becomes ln of u minus ln of 25 over u. And how can I simplify this? ln 25 minus ln of u. That's right. So you can write this as ln of u minus ln of 25 minus, well, this is a minus plus ln of u. 5 multiplied by 2u squared. I hope you guys follow that. The minus becomes a plus. I'm supposed to subtract the denominator when I expand this, but there's a negative in front. So when they distribute that negative, this becomes a positive. So you have 2 of these. So this becomes 5 over 2u squared plus 2 ln of u minus minus ln of 25. So I'm going to do a bit more of simplification here because I realize I can put them together actually, and it'll be a little bit better now. So I can write this as, I'm just going to write this as ln for now of u squared, right? Over 25. But I can write 25 as 5 squared. And I can rewrite this as ln of u over 5 squared. That 2 can be placed out in front now again, and this becomes 2u squared times 2 times ln of u over 5. So the 2's here cancel. And I'm left with 5 over u squared times ln of u over 5. And so this is my marginal density function. Okay, so we're just applying something that we've seen already to this new joint distribution, which is just a distribution of a set of new random variables based upon our previous original random variables. So it's just building on top of one another, this idea of joint distribution. Okay. All right, so let's do another one of these. So let x and y be independent and identically distributed uniform random variables on 0 to 1. And now the question is, suppose I have these new random variables, u equals 2x and v equals 3x over y. Find the new joint distribution of uv. Find what this is. Now, how do we interpret this statement here? X and y are independent and identically distributed. The identically distributed part is that each x and y are uniform random variables on 0 to 1. Both of them are random variables that are both uniform on the same interval 0, 1. And they're independent. Pardon me. Independent means that f of x comma y, remember this? This equals f of x times f of y. So, first of all, what is f of x? What is the density function for a uniform random variable on 0 to 1? And this is going to go the same way for f of y. Same idea. Do you guys remember the formula for the density function of a uniform random variable on the interval 0 to 1? So it's always going to have this zero otherwise business here, right? What's going to be the first term there, first branch of this piecewise function? And this is the simplest of all uniform random variables from 0 to 1. Right. So the formula is 1 over b minus a, but b minus a here is what? B minus a comes from the interval. And b minus a here is 1 minus 0, which is 1. So the joint density is just 1. That's it. And that's when x is between 0 and 1. And then it's also 1 when y is what? Between 0 and 1. So what's this going to look like? Well, it's going to look like 1 when this is true, and this will be 1 when this is true. So the joint distribution of the independent and identically distributed random variables will be what? Will be 1 when x is between 0 and 1, and when y is between 0 and 1. That's the only time. And then this will be 0 otherwise. See that? Now remember what the formula was of f of uv. It's equal to f of x comma y divided by the Jacobian let's see how did I have it earlier? The Jacobian. Yeah, the Jacobian x comma y. So this is the Jacobian of x comma y. So obviously here we're going to have a 1 because we just found that to be 1 within that interval. So this is a 1. Now the question is, what's the bottom? What's the Jacobian? So again, we have to set up this determinant which deals with the partial derivatives of the first function with respect to x, and then the first function with respect to y. Well, in this case, yes, y. And then the second function with respect to x, and then the second function with respect to y. And I want to find the determinant of this. So first I need to identify what is G1, what is G2. Remember, G1, G2 comes from these formulas here. So this is G of 1, xy. What is this? This is just 2x. And this is G of 2, xy, which is simply 3x over y. So then what's the derivative of G of 1 with respect to x? 2. And then what's the derivative with G of 1 with respect to y? 0. Pretty straightforward. And what's the derivative of G2 with respect to x? 3 over y, that's right. And then what's the derivative with respect to y? It's negative 3x over y squared. So then when you cross multiply this thing, right? Here, you're going to multiply these two things here together. But when you multiply these two entries here, they become 0 automatically. So you don't have to worry about that. So all we have is what? We got negative 6xy squared. And that's the Jacobian. But now I want to take the absolute value of that Jacobian. So it won't be a negative. It'll just be positive 6xy squared. And so we're putting that in the denominator. We're putting that over here. So then I get f of uv is equal to, well, if you do 1 over this, then this will result in the reciprocal. So this becomes y squared over 6x. Now, what's the issue here? The issue here is that we have we have an expression in terms of x and y, but we want u and v. That's right, hijab. So what am I supposed to do? How do I solve for x and y, or u and v in terms x and y in terms of u and v? We substitute, okay. So we have u again. U equals 2x, and v is equal to 3xy. I want to get u and v by itself. So what do I know about x? What is x? U over 2? Well, that was pretty easy. So x is u over 2. So every time I see x, it's really just u over 2. So I can place that now here. And I get 3 multiplied by u over 2 over y is equal to v. But I want to solve for y. So I can cross multiply this stuff and I get 3u over 2 equals v times y. I want to get y by itself, so divided by v, and I get that y is equal to 3u over 2v. Right? So now I can place that now, and I can replace that with the joint distribution function. So I know that y can be placed inside here, and I know that x can be substituted in here for. So I can write this now as f of uv, u comma v, and this becomes 3u over 2v squared divided by 6 times u over 2. And so this becomes 9u squared over 4v squared divided by 3u. And so then this becomes 9u squared over 4v squared multiplied by 1 over 3u. Why am I doing that? Because I'm keep changing and flipping. And so then the 3's here cancel. The u with the u squared cancels. And I'm left with my joint distribution, f of u, uv. And this is 3u over 4v. 0 otherwise. So now the question is, what's going to be the domain of this function here? Well, I know x is what? X is between 0 and 1. But then I know also x is what? U over 2. So I can replace that. And then what's u going to be between? what does u have to be between? 0 and 2, right? So 0 and 2 are the bounds for u. Has to be. Now, how about y? I mean, how about v? So let's look at what v is, or what y is. Y is 3u over 4v, right? 2v. But then 3u over, so I should say y is between 1 and 0. And then 3u over 2v, that's between 0 and 1. And we're looking for v. So what can I do? I can multiply everything by 1 over 3u. And so when I do that, I get 0 is less than or equal to 1 over 2v, which is less than or equal to 1 over 3u. If I multiply everything by 2, I get 0 is less than or equal to 1 over v, which is less than or equal to 2 over 3u. Now, I want to get an inequality with just v, not 1 over v. So how do I do that? So this is similar to saying like 0 is between 1 over x is between, for example, 2/3. So if that's the case, then what is x going to be between? And this can never be equal to it because you can never have a number here that will be equal to 0. Multiply by 2v. The thing is, if you multiply by 2v, if I multiply by 2v, what do I get? I get 0 is less than or equal to 1, which is less than or equal to 2v over 3u, right? If I multiply everything by 2v, so then, yeah, I think that would be, you can cancel the v's. Where can you cancel? You can cancel the v's here, right? This is u, not a v. Yeah. So you would have this. So actually, if that's the case, then from here, we can multiply everything by 3u. There's a whole bunch of multiplication going on. And we get that 3u is less than or equal to 2v. Or in other words, that v is greater than or equal to 3u over 2. Or in other words, v is greater than or equal to 3u over 2. So v is greater than 3u over 2. Yeah, it's a little rough here. So let me just erase this here. And, okay, so v is bigger than 3u over 2. So u is as big as, yeah. So U can be as big as 2 can be, and then so what's the maximum that V can be? V has to have a maximum because Y can be as big as 1. Um, and U can be as big as 2. So do you see what my logic here? So Y can be the biggest Y can be is 1. So that means that U, the biggest U can be is 6. So this 2. So this could the biggest that the numerator could be is a 6, and this is 2V. But actually, this is right because uh, the biggest that V can be is actually infinity, because Y can be as small as 0. It could get as close to as 0. In order for this to get close to 0, either U has to be really tiny, or U can be big, but V has to be really, really large, right? The bigger this denominator is, closer to infinity, the closer this becomes to 0. So yeah, this is correct. So then this here is my joint distribution here. And we can test all of this out just to double check that we did everything correctly. If we do the marginal distribution for each U and V and find whether or not that in itself is a PDF, which would integrate over everything and give you 1. So yeah, we can try that as well. So from here, can you find what f of v would be? What would be the marginal density of f of v? This was the joint density function we solved. This is the joint density function that we found, yes, for uv, because uv were variables or random variables in terms of x and y. We know what x and y are. They're independent and identically distributed random variables, uniform random variables on 0 to 1. And then we wanted to find what's the joint distribution or density function for this new set of random variables, which are in terms of the original random variables. So now I want to find the marginal density of f of v, and I'm utilizing the joint density function that we just found. Yes, we can integrate. How do we integrate? With respect to du, right? And u goes from, so this is f of v. U goes from 0 to 2 of 3u f 4v. So of course, what happens? The 3 over 4v is between 0 and 2 of u du. Right? And then we can integrate. This becomes u squared over 2 from 0 to 2. And then when we plug that in, we get 2, right? This whole thing here is just equal to 2, 3, 4v. So this becomes 6 over 4v, because this equals 2 when you plug in 2. And so this becomes 3 over 2v. This becomes f of vv. Okay, guys? Yep. Okay, great. So this is the nature of the game now. Finding the joint distribution of um, random variables that are functions of other known random variables. Okay, so let me see if I have one more of these. Mm, yeah. So we can stop with this. We can end with this one. Um, so in the few in the remaining time that we have, there's so much that we can still discuss about probability. Um, I guess before I let you guys completely go, no more Wednesday classes. I just want to make mention of a very important theorem in the theory of probability, and it's the central limit theorem. I've mentioned this a lot before, I think, here and there. The CLT. We're not going to go into the depths of it. We're not going to go into the proof of it. But this is a central aspect of probability. The central limit theorem basically states that if you take a sum of independent, identically distributed random variables, and if you take enough of those, if you have enough of those identically distributed random variables, the distribution of those independent sums of random variables is similar or becomes the normal distribution, which was that nice Gaussian curve. And the reason why it's so powerful is because the assumption of those independent random variables are not necessarily continuous. They could be discrete. They could be a mixture of continuous and discrete, as long as they're, well, no, they have to be both the same. So they're either discrete, all discrete random variables, or all continuous. But the thing is, it doesn't matter what distribution is it is. It doesn't matter if it's an exponential, a distributed random variable. It doesn't matter if it's a binomial. It doesn't matter if it's geometric. If you take a sum of those of the same kind, it approx as you get that number go to infinity, the idea is that it becomes similar, or it converges or becomes the normal distribution. So let me write that a bit more clearly in words, and then write that expression notation mathematically with the mathematical notation. So if there's a sum, so roughly speaking, this is a sum of independence of a large number. So the idea is large number. What does large mean? It means that you're approaching infinity. So a sum of a large number of independent random variables has a distribution that is approximately normal. Um, um, More mathematically speaking, let x1, x2, dot, dot, dot be a sequence of independent and identically distributed random variables. Each having a mean of mu and variance of sigma squared. Okay, so each one has the same mean and the same variance, obviously, because they're both identically distributed. They're the same random variable, just copies of them. So we have an infinite number. So this sequence is dot 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 means this continues on forever. So we have an infinite copy of a sequence of the same variable, random variable, having the same mean and the same variance. Then the idea is that the distribution of x1 plus dot 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 xn minus n times mu over sigma times the square root of n. This tends to the normal distribution. I should say to the standard normal. As n goes to infinity. Now, this may appear kind of strange, right? But this expression you've seen before. You've seen it before. I don't know if you guys recall from where, but remember when we talked about normal random variables, and then we found a way to standardize it. What did we do? Remember that? Z was equal to what? X minus mu over sigma. In doing so, this original X, which was a normal distribution, right? And this is what? This is the expected value of X. And this is what? This is the variance of X, right? When I did this operation, what did this become? What does Z become? This became the standard normal, where the expected value of Z is 0, and the variance of Z was 1. The idea now is that we don't have just one random variable, we have a sum of them. If we have a sum, so if we take the expected value of a sum of independent and identically distributed random variables, sigma is the standard deviation. It is. Oh, you're right. Pardon me. So this was the square root of the standard deviation. Pardon me. That's right. Square root of the standard deviation. Sorry, the square root of variance, which is standard deviation. That's right. Sorry about that. That's what I meant to say. I didn't mean to say variance. I meant to say the square root of the variance. But thank you. What this is saying, right? We're applying the same idea for a single normal distribution or normal random variable that we discussed. We're just applying this concept to a sum of independent, identically distributed random variables. It doesn't have to be normal random variables. It could be binomial. It could be geometric, it could be exponential, it could be Poisson. Doesn't matter what it is. If you have a large number of them and you add them up, and then you perform this kind of procedure here. So what is the expected value of a sum of random variables? What's the expected value? Well, isn't it just the summation of each of those random variables? But what's the expected value of one of them? The expected value or the mean of one of those, of each of these random variables is what? Mu. But I'm adding mu n times. So n times mu. So this is the expected value of the sum of these random variables. This is a sum, right? And then you can call this something else, but this is a sum of the random variables. And now what's the variance? What's the variance? You guys remember this? What's the variance? Well, they're independent and they're identically distributed. So only because they're independent, I can do this, right? Yes. Only because it's independent, I know that I can take the sum of all of them individually as well. The only reason why I can do this is because they're independent. If they're not independent, I can't do this. So only because independence. If they're not independent, then we're going to have something called covariance that appears. And that gets a little more computationally heavy. So each variance is sigma squared, but you have n of them. You have n sigma squared. So then when you take the standard deviation, which is equal to the square root of the variance, this is the square root of n sigma squared, which is sigma times the square root of n. And that's why we get this expression here. This is the standard deviation of the sum of the random variables. And again, the central limit theorem just says that this entire thing, as n goes to infinity, so as you take the limit, as n goes to infinity, this entire thing becomes the standard normal, z. That's what it becomes. And that's called the central limit theorem. It's a very fundamental theorem, and it kind of unifies all the random variables that you've discussed. It unifies all of them together, because what you're saying is, give me any type of random variable. I don't care if it's discrete or continuous, and give me a lot of the same kind. Give me, let's say, binomial. Give me 100 binomial random variables with the same mean and the same variance, and take the sum of those. That distribution, applying this kind of take the sum subtracted by the mean divided by the standard deviation, that is approximately the standard normal. And we have all this information about the standard normal. So we have all this information about this sum of independent, identically distributed random variables. Very deep theorem. Okay, so we're going to end our probability class with that. It's been real and it's been long. And there's so much more. There's so much more to delve into with probability. I hope that you guys developed more of a appreciation for probability and a bit more of insight into probability. Again, this is just an intro. There's much more theory to it. There's much more application to it as well. And all we've done is the surface. Do we still have Monday? I don't know. Did you say Monday? Is that what you meant, Mir?
I meant Monday, yeah.
We still do have Monday, but Monday will be more of a review. Nothing new. And Hijab, you are hitting it on the head. Machine learning, guys. I know there's a lot of computer science people here. There's a lot of machine learning people, um, or people that are interested in machine learning. So when people talk about, oh, what do you need to learn for machine learning, right? There's several mathematics subjects in mathematics that you need to know. One of them is probability. That's 1,000%. You need to know probability distributions, all the stuff we've done, and even more so, even more. The second thing is linear algebra. So there's a few students here that are taking both either simultaneously or within the same vicinity of each other in the semesters. Probability, linear algebra, the combination of those two subjects is foundational for machine learning. And then you also, for machine learning as well, need to understand vector calculus, particularly multivariable calculus, because there's this idea of optimization. The idea of optimization is embedded in the algorithms that some machine learning algorithms utilize. The idea of gradient descent, for example, is an optimization problem which can be explained through vector calculus, three-dimensional graphs, and that like. So for those of you who are interested in that field, I highly recommend linear algebra, probability, and multivariable. If you can master those three subjects in general, then when it comes down to learning the more nitty-gritty aspects of machine learning, it will be very useful and helpful for you guys. That's good, Hijab, that you're looking into that already with machine learning. Okay, so I want to also, we have a few minutes left. I want to give you guys a problem because that's just what we do, right? We just like doing problems and problems and problems. And I want to see what you guys think of it. Okay, it's nothing crazy. This may jog your mind a bit from the beginning of our class. And I just want to see what you guys think. So remember how we hold on, let me see. Wait, let me find the problem. This is not it. Oh, whoops. Okay, this is the one. So you remember how in the beginning of the semester we talked a lot about rolling dice and then finding the probability if you roll a dice, if you roll two die, if you wait, did I get that confused? Dice is plural, right? Or is it? I always get that confused for some reason. One
Dice is the
one
plural
die,
one.
two dice, right? Dice is die is plural.
No, the opposite.
I always get that confused for some reason. Because yeah, I think one, I'm pretty sure one die is singular. Okay, so we're getting two different. Let me just see dice. Yeah, dice is plural. Die is singular. Okay, die is singular. Yep. Yeah, the roll of one die. So we know. Remember we talked about that, right? In the beginning. Now I want to pose to you, now given all the probability that we've done, all the different random variables, and all the time that we've done spent after talking about a single die. Um, what happens if you have somebody named Una who rolls 6 standard, 6-sided dice and calculates the product of those 6 numbers? What is the probability that the product is divisible by 4? Does everybody understand? And of course, this is fair, okay? This is a fair 6-sided. I should have mentioned that. It's a fair one. So every side is equally likely, right? Just like a regular 6-sided die that we are accustomed to. But then this time we have 6 of them. So we have 6-sided dice, and we're rolling all of them at the same time. And then we calculate the product of those 6 numbers that appear when you roll it. The question is, what's the probability that the product of those 6 numbers is divisible by 4? And to you, I ask, how do we begin? I think this is manageable because we know what dice are. We know what it means to take the product of 6 numbers. And I think what you guys may need to know is, what does it mean to be divisible by 4? X mod. Wow, you're already talking about the mods. We need a 4 roll on the dice, or like 2 rolls. When the dice roll gives you at least a 4 or 2 2s. How about a 6 though? Can a 6 work? If you have a 6 and a 4, isn't that also a product? Or if you have a 6 and a 2, doesn't that also give you a product of 4? So it's not just when you have a 4 or when you have 2 2s. You can also have a 6 and a 2. And that product, 6 times 2 is 12. That's divisible by 4. This is a is this joint discrete random variables? You can think of it that way. Yeah, I like that. Do you make the chart with 1 1 1 2 6 6? No, because they're not going to be tuples. They're going to be 6 tuples. So you're going to have to do like 1 1 1 1 1, like 6 of them. And then it'll be 1, like it's going to be 6 times, it's going to be 6 to the 6th power. That's how big that chart would be. And so then you start to see, oh, that's kind of too much. I don't have time to write a 6 to the 6th entries in a grid. Should we do some prime factorization to all numbers in the die? Prime factorization might help. It might help. So there's a way to think about this, right? You can take at least a 4. At least one has to have a 4. But it gets a little tricky when 2 and 4s are involved. And then when 6s are involved. That becomes the tricky part. Right? So you can do it that way. You can do it from a more like a systematic way of directly finding the probability. But remember, there's a technique that we learned in probability when we talked about counting, that sometimes not finding it directly, yes, the complement. Sometimes the complement is a bit easier. So if I want to find the probability that the product is divisible by 4, just venture and think about and consider, is the complement easier to find? What is the complement? What's the complement of being not divisible by 4? Well, I think I just said it. The complement. You're not divisible by 4. So if you're not divisible by 4, then what are you? Do you guys understand what I'm saying? Again, this is the product. So you have 6 numbers that you multiply, and none of them are divisible by 4. There's a remainder, right? There's a remainder, yes. But what about those numbers in particular? So let me help you guys out. If you're not divisible by 4, for example, you can think of it as case 1. So we're using casework and complementary work. If the product is less than 4 or some odd number greater than 4. So for example, if you're not divisible by 4, 4 doesn't appear as a factor of that product. And or you can also say 2 squared doesn't appear in the prime factorization of the product. So that only happens if all the numbers are odd. Right? What if you're all odd and you multiply all odd numbers? Is it ever possible to be divisible by 4 if you're all odd? Well, if you're all odd, 2 is never even mentioned. Because if it were mentioned, if 2 was a factor of a number, then it wouldn't be odd, it would be even. So if you're all odd, then that's it. It's not divisible by 4. So what's the probability that all of them are odd? Well, if one of them is a half, right? You have half of them being odd numbers, 1, 3, and 5, but you have 6 of them. So 1/2 to the 6th power will give you 1/64, right? So that's the probability that all of them are odd, but that doesn't just because they're all odd doesn't fully cover the realm of the product not being divisible by 4. This is if all the numbers are odd, so there is no divisibility by 4. But there's also one more case. There's a case when the product is divisible by 2, but not by 4. And how is that, pardon me, how is that possible? That it's divisible by 2, but not by 4. Less than 4. So you know what? I'm gonna leave this to you guys. I want to see who's able to solve this for Monday. Okay, so consider this case. Once you have this case, you'll know what to do with in terms of putting it all together. But this is a very nice problem that incorporates all these different counting techniques that we discussed in the beginning of the semester. That I thought was pretty neat. And let me just say, this is a competition problem for high schoolers. So this is something that they expect high schoolers that are really motivated in mathematics to know how to solve for probability. Okay. Anyways,